Well, howdy there, year 9 and 10. I don't know about you, but this here lockdown's got me going crazy. I just put on this cowboy hat, walk around the house, pretend to be a cowboy. Sometimes I walk out around Hastings, pretend to be a cowboy too. I'm only joking. I haven't really gone crazy, and I don't really walk around the house pretending to be a cowboy. Most of the time. Anyway, welcome back to this week's online physics lesson. This week we're going to be doing CP2 Forces. We're going to go over Newton's 3 laws of motion. Now, I've had a look and we've got about 4 or 5 lessons left to go until the end of term. So, by my calculations, if we do 1 lesson on each topic in paper 1 of physics, then by the end of term we will have covered all of the topics. We'll touch upon all of the topics in paper 1 for physics, which will enable us to do a mock paper 1 for physics. I think this will be really great because it'll be a really great summary for the year and will give you guys a sense of achievement for all of the fantastic work that you've been doing this term and last term during the online lessons. So Miss Page has already touched on CP1 motion. This week we'll do CP2 forces. Next week CP3 energy. Following week CP4 waves. Week after that CP5 electromagnetic waves. And we've already done 2 lessons on CP6 radioactivity. So we will have touched on all of the topics in CP1 for physics, paper 1 physics. Okay, let's get started with this lesson. So we're looking at Newton's first, second, and third laws of motion, which is part of CP2 forces topic. I think it'll take us about an hour to complete it, although I'll try and go fast to speed that up. The equipment you'll need is a pen, paper, scientific calculator. Ideally, if you don't have one, you can use the one on your phone. And ideally, a quiet, clear workspace. If you don't have any of these things, can you please pause the video and go and get them now? Okay. So let's move on. Just quickly, work expectations from St Leonard's Academy Science Department. I know we do it every time, but if you're just joining us for the first time, we would like you to try to complete 3 hours of science work per week, and that can be the revision booklets that we've given you, it can be online lessons such as this one, or it can be your own work, for example, using BBC Bitesize or Oak National Academy. Let's have a bit of a recap on forces. What is force, mass, weight, what's acceleration, and so on. Okay, so when I say, I'd like you to pause the video and try and match the words on the left with the definitions on the right. When you've done that, or especially if you find it easy, and if you're a higher or a triple student, then do the purple task. Try to use the 3 keywords that we've got along the bottom in a sentence, in 1 sentence. Okay, you can pause the video now. I will assume that you paused the video and we'll just move on. Okay, your answers. If you hadn't paused it, then do so now and do the task. Okay, let's go through the answers. Force 1 is a push, pull, or twist which changes an object's speed, direction, or shape. The unit is newtons and it is a vector quantity. Remember, a vector has a size and a direction. Mass is a measure of the amount of material in an object. The unit is kilograms and it is a scalar quantity. Scalar quantities only have a size. Weight is the force pulling an object down due to gravity, due to its position in a gravitational field. The unit is newtons and it is a vector quantity. Stationary is a big word which means not moving. And acceleration is a measure of how quickly the velocity of an object is changing. The units are meters per second squared, that is meters per second, and it is a vector quantity. Okay, Newton's first law. We've got a ball, it's floating on the water. The ball is not moving. what forces are acting on the ball. I'm going to go through it, but you might like to pause the video and draw what forces are acting on the ball or in the water. You can pause the video now. Okay, forces we've got. We've got the weight of the ball is acting down into the water. If there was only the weight of the ball acting, then it would sink into the water. It would accelerate down into the water, but there's something acting back up. We've got buoyancy force acting back up from the water. Now, these forces are balanced. That means they are of equal size. You see the arrows are of equal size, but they're acting in opposite directions. This means if we were to add those two forces up to get the resultant force acting on the ball, the resultant force on the ball would be 0. If the resultant force on the ball is 0, and i.e. the forces are balanced, then it will stay not doing what it's doing. It will stay not moving. We could use the example of a book on a table as well. We know that the force of gravity is acting on the book, so we have weight is acting down, weight force. The book doesn't fall through the table, so there must be something acting back up. We've got the normal force from the table is acting on the book. Again, the forces are balanced, i.e. they are equal in size, but acting in opposite directions. If the forces are balanced, then when we add them up, there will be no resultant force, and the book will stay stationary. It will stay not moving. Okay, let's add in an unbalanced force. I jump into the pool, and I go forward with my fist and smack the ball. Now, there is an unbalanced force acting on the ball. When we calculate the resultant force, i.e. when we add up all the forces acting on the ball, we will have a force left over. So, calculating the resultant, if I add the weight of the ball and the buoyancy force from the water, they are equal and opposite. So they cancel out to 0. So the force acting in the vertical direction is 0. There's no force acting backwards on the ball from my force from my fist, and so the ball will accelerate to the left. If, when I add up all the forces acting on an object, there is a resultant force, then the object will accelerate in the direction of the force. So Newton's first law. Newton said, if an object is stationary, i.e. not moving, and the forces on it are balanced, i.e. they're all equal and opposite, then the object will not move. If the forces on it are unbalanced, the object will move. It will accelerate in the direction of the resultant force. Don't worry, you don't have to copy that down. We have an exercise later where you will copy something similar down. Okay, now Newton's first law also deals with objects which are moving at a constant velocity. So here we've got a car on the motorway. It's driving at a constant speed, a constant velocity. Acting backwards, we're going to have air resistance and friction from the road. Acting forwards, we've got the driving force from the engine. Now look, those arrows are equal in size, but they're opposite in direction. They balance. We're going to have the weight of the car acting down, and unless the car is accelerating down into the road, then we'll have a normal force acting back up from the road. These forces, if we add them all up, the weight of the car is balanced by the normal force from the road. The driving force from the engine is balanced by the air resistance and the friction. If we add up all these forces to get the resultant force, we will get 0. The resultant force is 0, and so the car will stay moving at a constant velocity. This might sound obvious, but this was really quite revolutionary at the time when Newton came up with it. He basically said, if an object is moving and no resultant forces act on it, it will stay moving at a constant velocity. Before him, people thought that you needed to continually put force in to keep something moving. Okay, now let's imagine that the driver puts their foot on the floor. they push down the accelerator. So again, we've got the weight of the car acting down, just the same. Normal force acting back up, just the same. Air resistance and friction is exactly the same as it was before, but now, because they've pressed on the accelerator, we've got a larger driving force from the engine. Now, when we add up all these forces, we are going to have a resultant force. So normal force and the weight of the car are equal and opposite. They balance. So they will, if we add those together, they will add to 0. Air resistance and friction is a small arrow. It's a relatively small force compared to driving force from the engine is a much larger arrow in the horizontal direction. If we add up the resultant force from the engine and the air resistance acting backwards, then we will have a force left over acting to the left. The resultant force. This makes sense. There is more force acting to the left than there is acting to the right. And so if we add them together, we will have some force acting to the left. That's our resultant force acting to the left. We've got a resultant force acting to the left, and so the car will accelerate. It will change its velocity to the left. So, if an object is moving, Newton's first law says, if an object's moving and the forces are balanced, the object will stay moving at a constant velocity. If an object's moving and the forces on it are unbalanced, the object will accelerate in the direction of the resultant force. Remember, balanced forces are forces which are equal in size, acting in opposite directions on the same object. Okay, I'd now like you to watch the video, the YouTube link below. It's a great video about NFL players taking the ball, running fast, smashing into each other, and seeing how resultant forces affect the motion of objects. I'd like you to, when you watch that video, try to answer this question to the left. How does inertia affect an object's motion? So keep an eye out for inertia in the video and answer, how does inertia affect an object's motion? Okay, I'll put the link to this below the YouTube video. Okay, so this YouTube link will be below this video. Okay, you can pause the video now. Okay, hopefully you enjoyed that. It's a fun video, making physics fun, spelled with a PH, not with an F. So inertia, if you did that, inertia is an object's mass and its movement times together effectively. So the larger something's inertia, the more force I have to put in to change its velocity. If something is very large, very massive, and moving very fast, then it will have a lot of inertia, and it will take a lot of energy. It will take a lot of force for me to change its motion. Okay. Here we've got some examples of free body diagrams with forces acting on them and a current state of motion. I will do the first two with you, and then you can do the next two. If you know how to do this, by all means pause the video right now and just go through them and then check your answers when we go through. Okay? So in A, we have an object, as shown. The object is represented by the square, by the rectangle. It's stationary at the moment. It has a 25 Newton force acting down and a 40 Newton force acting up. Remember, newtons are the unit for force. In the case of A, if we add up the forces acting on it, it's got a greater force acting up than it does acting down, so it will have a resultant force acting up. The resultant force will be 15 newtons. We don't have to worry about that, really. All we have to know is that there is a resultant force acting up. It's stationary at the moment. What will happen? It will accelerate upwards because there is a resultant force acting upwards. In B, the object is already moving at a constant speed, we can assume. It has 25 newtons acting down and 25 newtons of force acting up. These forces are balanced. They are equal in size and opposite in direction. The forces are balanced, which means the resultant force will be 0, if we add them up, which means the object will continue moving at a constant velocity. It'll just keep on doing what it's doing. I should say velocity, not speed. I apologize. Okay, now I'd like you to pause the video and have a go at C and D. Okay, do exactly the same as what we were doing. C is stationary at the moment, and D is currently moving to the right. Pause the video now. Okay, let's go through. Object C, the forces acting in a vertical direction, up and down, will balance. 25 newtons up, 25 newtons down. They balance, so if we add them up, they will add up to 0. There is, however, a resultant force. There will be a force left over of 10 newtons to the right. There's no force acting to the left. There's no balancing force. So there is a resultant force of 10 newtons to the right. It's stationary at the moment. With these forces on it, the object will accelerate to the right. D. The forces acting in a vertical direction, we've got 25 newtons up, 25 newtons down. They balance, so they will add to 0. It has a larger force acting to the left, 20 newtons, than it has acting to the right, which is 10 newtons. So if we add these forces acting in a horizontal direction, there will be a resultant force acting to the left. The object is currently moving to the right. What will it do? It will accelerate to the left. Now, this gets a bit complicated. Because it's moving to the right already, by accelerating to the left, it will in fact be slowing down. So the object is moving to the left currently. It has an unbalanced force, has a resultant force to the left, so it will accelerate to the left, i.e. it will slow down. Don't worry if you don't get that. Perhaps rewind and go through the explanation again. Okay, so this is why I said not to copy down the definitions earlier, because we've got the definition here. What I'd like you to do is to pause the video when I say, and to fill in the gaps with words at the bottom of your screen. If you finish that, and it's too easy, have a go to try to explain this purple question. What will happen to this astronaut in space? They've just been let go from their spacecraft, so you can assume the spacecraft is orbiting around the Earth, and the astronaut has just let go of their spacecraft. What's going to happen to them? Okay, pause the video now. Let's have a go. Okay, copy and complete. Your answers should be Newton's first law states that if all forces are balanced on an object, then the object's motion won't change. This means if the object's stationary, it will stay still. If an object is moving, it will keep moving in the same direction and at the same speed, i.e. same velocity. If the forces are unbalanced and there is a non-zero resultant force, then the object accelerates. This means if an object is at rest, then it will start to move. If an object is moving, its movement will change. Okay, and the astronaut in our purple task here, the astronaut will continue orbiting around the Earth. Okay, so they're moving great speed around the Earth, and there's no atmosphere in Earth, there's no air resistance to slow them down and to stop them from moving. So they continue to orbit at a constant speed. Now, you might say that their velocity is always changing, and their velocity is always changing because there's an unbalanced force acting towards the center of the Earth due to gravity. So the astronaut is always accelerating towards the center of the Earth. That keeps them moving in a circle. But they're always moving at a constant speed because there's no air resistance to stop them from moving forward around the Earth. Okay, Newton's second law, the theory. Let's just think about this first. Which one of these situations is going to require more force? I've got a 13 kilogram ball in one hand, I've got a 9 kilogram bowling ball in the other hand. I'm going to accelerate my 13 kilogram ball at 3 meters per second. Put in some force and give it that acceleration. Or I'm going to accelerate my 9 kilogram ball at 3 meters per second. So the acceleration is the same. Which one do you think is going to require more force? Pause the video, have a think, give it an answer. Okay, if you said the 13 kilogram ball, you would be right. It's going to take more force to accelerate a more massive object at the same acceleration than it takes to accelerate a less massive object at the same acceleration. So the mass of an object affects how much force I need to put in to get a certain acceleration. Now, how about this? Which one of these situations takes more force? Now I've got two balls of the same mass, 8 kilograms, and I'm going to accelerate one at 3 meters per second squared, 3 meters per second, and I'm going to give the other one a much higher acceleration of 5 meters per second. Which do you think is going to take more force? Pause the video, give it a think, and answer. Okay, if you said 5 meters per second, 5 meters per second squared requires more force, you'd be correct. If Newton said, if I have an object of the same mass and I wish to give it a larger acceleration, I need to put more force in, which makes sense. Let's put these two together into Newton's second law. Newton said that if I have an object of a certain mass in kilograms and I apply a certain force to it in newtons, then it will give the object a certain acceleration in meters per second squared. If I double the force on that object, then I will double the acceleration on that object. If I double the mass of an object, but I keep the force of the object the same, the force on the object the same, if I double the mass, then I will halve the acceleration. Okay, putting that all together, we get force, or resultant force, in newtons is equal to the mass of an object in kilograms multiplied by the acceleration of the object in meters per second squared. F equals m times a. Force equals mass times acceleration. Okay, you can now write down that equation. This is Newton's second law. The acceleration of an object depends on its mass and the resultant force acting on it. And we can write this, if you're comfortable rearranging equations, you can just write down the equation. If you prefer to use equation triangles, you can write down this equation as an equation triangle, FMA. Now this equation only works if we keep the units the same as they are written here. Newtons, kilograms, meters per second squared, i.e. meters per second. Okay, let's do some trial calculations. I'm going to go through these two with you, and then I'll have two more which you can do yourself. If you want to do this yourself, this is too easy, then simply pause the video now and answer these questions, and then check that you're right. Question 1. What is the resultant force needed to make a Snorlax accelerate at 2 meters per second squared? The mass of a Snorlax is 460 kilograms. Careful, we need to use a mass in kilograms. Luckily here it is in kilograms, so no conversions required. Okay, I'm being asked for the force. So if I'm using my equation triangle, I cover F, and I have left at the bottom M times A. M and A, M times A. F equals MA. The force is going to be equal to the mass times the acceleration. The mass is 460 kilograms. The acceleration is 2 meters per second squared. So our force is going to be 920 newtons. Make sure to put the units. Question 2. What is the inertial mass of an object which accelerates at 5 meters per second when a resultant force of 125 newtons is applied. So they're asking us for the mass now, and they're giving us the acceleration and the force. Using an equation triangle, I can cover up the mass and see what I have left. Cover up mass, and I have F over A, F divided by A. So mass is going to be equal to F over A. My force is 125 newtons. My acceleration is 5 meters per second squared. And so my mass is going to be 125 divided by 5, 25 kilograms. Remember always to put the unit. Okay, now it's your turn. I'd like you to try to do these calculations. Be careful, this mass is in grams. You're going to need to convert it to kilograms. Give you a little hint. So you should be able to do that from our key skills lesson. If you didn't do the key skills lesson, then do please go back and do the online lessons on key skills part 1 and 2. However, just in case you didn't do it, I can tell you that to convert from grams to kilograms, you need to divide by 1,000. So, pause the video and give it these two questions a go. Use F equals ma triangle here, or the equation. Pause the video now. Okay, I'm going to assume that you paused it. Let's go through the answers. For A, the mass of Pikachu, 6,000 grams. They're asking us for what's the force needed, so we're going to have F equals m times A. The mass is 6,000 grams, which is 6 kilograms divided by 1,000. 6,000 divided by 1,000 is 6 kilograms. The acceleration is 6 meters per second squared, so F equals m times A. Mass, 6 kilograms times 6 meters per second squared acceleration is going to be 36 newtons. And B, what is the inertial mass of Rapidash, which accelerates at 8 meters per second squared when a resultant force of 640 newtons is applied? No conversions required for this one. We just need to do m equals F over A. Mass equals force divided by acceleration. 640 divided by 8 is 80, and the units for mass are kilograms. Boom. That was Newton's second law. Don't worry if you don't think you had enough practice. We've got a little bit more practice at the end. Newton's third law, then. Okay, why don't we fall through a chair that we're sitting on? Imagine you're sitting on a chair right now. I assume you probably are. Why don't you fall through it? This might seem on the surface similar to balanced forces. However, this is a bit different. My weight acts down on the chair. Yep, my weight is acting down on the chair right now. I don't fall through the chair, so that must mean that the chair is pushing back on me. Okay, so I act on the chair, and the chair acts on me. In this case, the chair couldn't cope, and this man's falling through. We can think of, again, our book on the table. It's not moving. Okay, we have the action force, which is the weight of the chair, the weight of the book acting down. We have on the table, and then we have a reaction force, which is acts from the table back up. Why don't we fall through the chair? The chair pushes back with an equal and opposite reaction force. Now, this might seem very similar to Newton's first law, which said that if the forces on an object are balanced, then it will stay stationary. Balanced forces from Newton's first law are equal in size and opposite in direction, but they act on the same object. Action-reaction force from Newton's third law is talking about forces which are equal in size, opposite in direction, but acting on different objects. So, the weight of the book acts on the table acts back on the book. Two different objects. Newton's third law, action and reaction. What I'd like you to do is to, when I say, to pause this video and to watch the YouTube link here. I will include it below this YouTube video. Newton's third law comes in at about 2 minutes. so you can fast forward to 2 minutes. However, I encourage you to watch the whole video because it goes through Newton's first, second, and third laws. When you watch the video, I'd like you to write out what is Newton's third law in your own words, and to give examples of action-reaction pairs from the video. Okay, so hopefully you've got an example of Newton's third law. If you haven't paused and done it, then please pause the video now and watch that video. We'll go through what's Newton's third law in just 1 second. Hopefully you have a definition down. Examples of action-reaction pairs from the video are a bouncy ball acting on the earth and the earth acting back on the bouncy ball, and a bike tire pushing on the ground, pushing on the earth, and the earth pushing backwards on the bike tire, pushing the bike forward. Newton's third law. Often it's shortened down to every action has an equal and opposite reaction. So if that makes it easy to remember, you can remember it like that. However, because we're physicists, because we're scientists, we like to be precise. And this, every action has an equal and opposite reaction. It doesn't tell us that it's acting on different objects. So I'd like you to include this bit below. Whenever two objects interact, they exert equal and opposite forces on each other. So whenever two objects, and they can be touching, these can be contact forces, these can be non-contact forces, like gravity acting on a satellite. Whenever I put a force onto something, it does exactly the equal and opposite force backwards. Let's have some more examples of action-reaction pairs. Okay, pushing a pram. Here's a lady doing a marathon with a pram. Very impressive. So she is pushing the pram forwards, of course. Here we go. Now the pram is also pushing backwards on her. That's why you feel a force pushing backwards as I'm pushing forwards. These forces are equal in size and opposite in direction. Action-reaction pairs. Another example. Car tire on the road. Car's pushing forward. The car engine is going, is putting force to the tires. There are contact forces between the tire and the road. The tire pushes on the road backwards. Yeah? As the tire spins, using the force of friction, it pushes the road backwards. The road pushes back forwards on the tire, and that pushes the car forwards. These forces are equal in size and opposite in direction. One more example of an action-reaction pair. A satellite in Earth orbit. Okay, there are non-contact, here we go. There are non-contact gravitational forces between the Earth and the satellite. The Earth pulls on the satellite. The satellite pulls back on the Earth. These forces are equal in size and opposite in direction. Now the Earth, it's worth noting that the Earth is much, much, much more massive than the satellite. So if the satellite were to stop orbiting around, if you were to put force acting to the left, then the satellite is going to move towards the Earth much faster than the Earth is going to move towards the satellite, because the Earth is so much more massive. It has so much more mass than the satellite. Okay, let's have a go writing out Newton's third law again in a different way, but with an emphasis on spelling and grammar. I would like you to find all of the spelling and grammar mistakes you can in this sentence, in these sentences rather. So when I say I'd like you to pause the video, write these out, correcting every single mistake. And we'll go through in just 1 second. Okay, I think there are 10 or possibly more, but we'll find out when we go through. Okay, you can pause the video now. Let's go through. So hopefully you got these. Newton's should have an apostrophe because it's his law. Third law should be capitalized because it's a proper noun. Third law. Newton's third law states that for every action, there should be an I there, A-C-T-I-O-N. There is an equal and opposite should be two P's for opposite, O-P-P-O-S-I-T-E, reaction. For example, when a rocket takes off, this should be two words, so put space in there. It exerts a downwards force. That doesn't look right. Downwards is spelled with an A, not an O. So D-O-W-N-W-A-R-D-S. Force on the air. The air, there should be a full stop here after air. The air then exerts an upwards. Again, this should be an A here, U-P-W-A-R-D-S. Force on the rocket, pushing it up. And then last one, action. This should be capitalized, it should be a capital A. Action, reason. There should be, reaction is spelled wrong here, R-E-A-C-T-I-O-N. Reaction. Pairs are not the same as balanced forces. There we go. So as it says, action-reaction pairs are not the same as balanced forces because they act on different objects. Okay, let's do some practice questions. You might think that all, no, I don't think you probably do think that's simple, but have a go at these questions and we'll go through afterwards. I'll do the first, help you with the first two, and then I'd like you to do the rest yourselves. I will give you the answers though. So when you walk, your foot pushes backwards on the ground. The force of your foot on the ground is part of an action-reaction pair. Your foot pushes backwards on the ground. What is the other force in the pair? 1AI. The other force in the pair is the force of the ground pushing forwards on your foot. AI. 1AII. What effect does this force have on you? It pushes you forwards. Okay, so when I'm walking, I push backwards on the ground pushes forwards on me, and I move forwards. The ground also moves backwards a tiny, tiny, tiny amount. But because the Earth is so massive, it's almost negligible. But the Earth does move backwards. Okay, have a go at the rest of the questions. And we'll go through in just 1 second. So you can, when I say pause the video and have a go at the questions, you can pause the video now. Let's go through. Okay. AII, why is it more difficult to walk on icy ground? Icy ground has a lot less friction than a rough surface. Okay, so I can't exert as much force on the ground because the force of friction will be much lower. If I put a large force, my foot will just slip. What effect does the force have? What effect does the force from your foot have on the Earth? Oh, we went through that. It will push the Earth backwards a tiny amount. I get pushed forwards, the Earth gets pushed forwards, gets pushed backwards. Why don't we notice this effect? Because the Earth is so massive. Write down two similarities between balanced forces and object. I'm going to put the answers up here for you. Okay. So 2A, two similarities between balanced forces and action-reaction pairs. Both have forces of equal magnitude but opposite direction. Those are the two similarities. Two differences: balanced forces act on the same object, action-reaction pairs act on different objects. What effects can balanced forces have on an object? Balanced forces can keep it stationary or keep it moving at a constant speed. Action-reaction pairs, they can accelerate an object. They can also keep it stationary as well, it should say there. So keep something stationary, or keep it, or accelerate it, or keep it moving at a constant speed. All depends on the other forces acting on a body. Okay, a little bit more practice then. Action-reaction pairs or balanced forces. Decide if these statements apply to action-reaction forces, balanced forces, both, or neither. I'd like you to write A to F on your page. and write action, reaction, balanced forces, both or neither for these 6 statements. You can pause the video and do that now. Okay, let's go through. Do these statements apply to balanced forces, action, reaction forces, both or neither? A, the forces are equal, that is both. The forces are different sizes, neither. They're always the same size. The forces act in the same direction, neither. The forces in balanced forces and action-reaction pairs act in different directions. The forces act in opposite directions is both. The forces act on the same object is balanced forces. The forces act on different objects are action-reaction pairs from Newton's third law. Okay, we're there. We're finished. Quick summary. Well, we've got a few extra little questions to do, but quick summary for if you haven't got one of the laws, Newton's 3 laws. The first law, an object will remain in the same state of motion unless a resultant force acts on it. I.e., if it's stationary, it will stay stationary. If it's moving at a constant velocity, it will stay moving at a constant velocity. If a resultant force acts on it, it will accelerate in the direction of the resultant force. Newton's second law, F equals ma. Resultant force in newtons is equal to the mass of an object multiplied by the acceleration of that object in meters per second squared. The acceleration, we could say it as well as the acceleration of an object depends on its mass and the resultant force acting on the object. And Newton's third law, every action has an equal and opposite reaction. Or, a more scientific wording, whenever 2 objects interact, they exert equal and opposite forces on each other. If you haven't got any of these laws down, do please pause the video and copy them down now. Okay, exit ticket. We've got 4 different questions, okay? We've got 1 question on each of the Newton's laws, and a 4th one for students who wish to test themselves, really push themselves. So here we've got a helicopter. It's got a force acting left, a force acting right, a force acting up, force acting down, and it's moving forwards at 100 meters per second. Moving to the right at 100 meters per second. Look at the drawing, look at the forces acting. What is the resultant force in a horizontal direction? That is, if we add up all the forces in a horizontal, that is left to right direction, what is the resultant force? B, what will happen to the speed of the helicopter in the horizontal direction? That is, to the left and right. Will it speed up? Will it slow down? Will it stay moving at a constant velocity? Constant speed, constant velocity. What is the resultant force in a vertical direction, i.e. upwards and downwards? Add up the force acting down and the force acting up, and will there be a resultant force upwards or downwards, and what will the size of that force be? And D, what will happen to the velocity of the helicopter in the vertical direction, i.e. up and down direction? I'm not worrying about left and right. Question 2. Here we're using our F equals ma equation, okay? 2a, a jumping flea has an acceleration of 2,000 meters per second squared. The mass of the flea is 0.5 milligrams. Calculate the force exerted by the flea as it jumps. You're going to have to convert 0.5 milligrams into kilograms. You've been given a hint. 1 milligram is 0.000001 kilogram. I will help you out that conversion. To convert 0.5 milligrams to kilograms, you need to divide this by 1 million. Okay, divide that by a million and write out F equals ma. And then use F equals ma to calculate what the force will be in this situation. B, a man accelerates at 15 meters per second squared when doing a high jump using a force of 1,200 newtons. What is his mass? So again, write out F equals ma, rearrange for m, or use your equation triangle, put in the numbers, and calculate the mass of the man. C, a racehorse has a mass of this, 500 kilograms. It exerts a force of that. What is its acceleration? Cover acceleration, and see what you have left. You'll have F over m. Put in the numbers and calculate the acceleration. Question 3. So here we are. This is Newton's third law, action-reaction pairs. Two boys are pushing on each other. They are not moving. Al is putting a horizontal force of 40 newtons on Ben. Explain what force Ben is putting on Al. So they are not moving. So what must the force of Ben be on Al? Describe the action-reaction forces between Ben and the ground. If Ben is not moving, what force must he be putting on the ground, and what force must the ground be putting on him? Have a think. And see which two of the four forces in parts A and B explain why Ben is not moving. Explain your answer. What must be the case if Ben is stationary? Think about Newton's first law. Okay, and perhaps balanced forces might be important. And have a go explaining your answer. Question 4 then, and this is just as an extension task for higher or triple students. We haven't gone over this explicitly, this example. It's about changing direction. It's about changing velocity, changing direction, which, remember, if something is going at a constant speed but changing direction, it is in fact accelerating. When an aeroplane turns, it needs to fly at an angle like this. Explain why this is necessary. Think about unbalanced forces, think about acceleration, think about changing velocity, and think about when something changes direction, is it changing velocity? Okay, 3 points for that, 3 marks. Submit your answers to showbie.com using the same class code HZ9N9. The due date for this work is Tuesday, the 16th of June. If you've made it to the end of the video, thank you very much for your attention, and I look forward immensely to seeing you all next week when we do CP3 energy. See you again. Howdy. I don't know what cowboys say for goodbye. Howdy. Pass. You can include it in your answer if you like. Goodbye.